I want to make a note here. This curve actually lies on a surface. So note, this curve is called an elliptical helix. It lies on the cylinder given by ... We're going to figure out what kind of cylinder it is. So let's figure out what that cylinder has to look like. Let's figure out the equation of that cylinder, the rectangular equation. And I'm going to remind you of some skills you learned in Calc 2, most likely, maybe pre-calc. Remember, we can think of this guy as x, right? And this guy as y. We only think of this guy as a vector, this whole thing as a vector when it's convenient, when we want to use vector operations. But really, we think of it as a set of points, the tips of the vectors, right? Most of the time. So this is a set of points. Oh yeah, a curve is a set of points, right? That makes sense. So would you believe then if I create the related parametric equations x equals 3 cosine t and say y equals 4 sine t, I can eliminate the parameter using some techniques that you learned last semester and then fiddle around with the t, the z component rather, to figure out what the surface actually looks like. And that surface, the curve is going to lie on. So let's forget about the third component. Let's pretend like this is in the plane for right now. If you looked at this thing from above and couldn't see the height component, it would look like an ellipse, wouldn't it? It was centered at 0, 0, and you'd go out on the y-axis from the center 4 units to get to the edge of the ellipse, and on the x-axis, left or right, you would, if you're looking at it from above with the usual orientation, left or right, 3 units. It would look like an ellipse. So let's remind you of something you did back in Calc 2 to eliminate the parameter and figure out what the rectangular equation of the ellipse was, and then we'll convert it to a cylinder in space. So remember what you did? You solved for cosine and sine in these cases. Does that sound familiar? So if x equals 3 cosine of t, then x over 3 equals cosine of t, and y over 4 equals sine of t. And then to figure out the equation of the ellipse, you used a very familiar, probably your favorite trig identity, if you had to pick a favorite. Right? Anybody remember what it is? So remember the identity. I'll just use a generic form of it. Let me use cosine squared theta plus sine squared theta equals 1. In this case, cosine is x over 3. Bless you. So x over 3 squared, right? I'm just plugging x over 3 in for this identity, which I know is true. If x over 3 equals cosine of theta or t or whatever you want to use, I can plug that in, right? And then, in other words, cosine squared t plus sine squared t has to equal 1. So I'm plugging it into that expression, right? So based on, I just wrote the identity down generically here, but basically I'm plugging it in here, cosine. Oops, that should be sine. Okay? Now, I'm going to add that to, okay, sine of t is y divided by 4. And then I know that has to equal 1. Usually, you write the standard form like this. If you square both the numerator and denominator of both fractions, you get x squared over 9 plus y squared over 16 equals 1. Did you buy that? Okay, now let's uncross out the z. So z is t over 2. That division by 2 doesn't matter. Z can range between all real numbers, right? So what you would do, the way you would think about this, you would think about this curve as your generating curve for your cylinder. For, whoops, can't spell today, cylinder. Okay? And since z can range between all real numbers, z ranges Z can be any real number. Think of translating that generating ellipse up and down parallel with the z-axis. You've created an elliptic cylinder, right? So that's what I mean when I say this curve right here must lie on that elliptic cylinder. And that surface then is, it kind of looks like the tin can shaped cylinder, but remember it's, that generating curve is, so say that's the generating curve, it's really an ellipse, it's not a circle. Now imagine taking that generating curve and moving it up and down. The z value is allowed to range, so move it up and down. Do you see the cylinder? Let me take a copy of that. If you move it up, down, copies of it up, down, to infinity and beyond, as Buzz Lightyear would say, you would generate this elliptical cylinder. And so what we're saying then is that that spiral shape lies on, it must lie on that cylinder. Well, I should make that part dotted, so the part in back goes dotted, but you get the idea. Whoops, I went a little off course there. Hey, yeah, you try it. You laugh at me. Okay? Well, how do I know that that curve lies on the cylinder? Let me put it this way. The points that make up the helix are solutions to the equation of the cylinder. And therefore, the graph of the helix lies completely on the cylinder.